Well, there are a few things about the integrals that are still to be discussed. If you remember, in the last class we had discussed what is meant by function of a bounded variation, and the whole idea there was that till then we had discussed the integrals of this type. We had discussed integrals of the type integral a to b f d alpha, where we had always taken alpha as a monotonically increasing functions, okay. And the crux of the discussion in the last class was that we can replace the class of monotonically increasing functions by a class of functions of bounded variation, okay. And every real valued function of bounded variation can be expressed as a difference of two monotonically increasing functions, and hence if this alpha is a function of bounded variation, and if you write this alpha as alpha 1 minus alpha 2, where both of these are monotonically increasing, then you can define this integral as integral a to b f d alpha 1 minus integral a to b f d alpha 2, okay. That was the idea, okay. And then what we said was that the main purpose of doing this thing is that we want to prove something what is called integration by part, where we have to convert the integral f d alpha into integral alpha df, okay. And for that both the things have to be defined, integral f d alpha and integral alpha df, and that is what we want to do now, okay. So that is integration by parts. Okay. So here is, let us say that suppose we take two functions, suppose f from, let us say f and alpha both are functions from a b to r, and suppose both are functions of bounded variation, f alpha from a b to r are functions of bounded variations. Functions of bounded variation. And let us say that suppose both the integrals exist, that is integral f d alpha also exists and integral alpha df also exists, okay. And further assume that integral a to b f d alpha and integral a to b alpha df exists. That means f is Riemann Stieltjes integrable with respect to alpha and alpha is Riemann Stieltjes integrable with respect to f. Suppose both these things happen, okay, then integral a to b f d alpha, that is equal to okay, f b alpha b minus f a alpha a and minus integral a to b alpha df, okay. Of course this integration by parts is something that you would have also seen in the undergraduate calculus courses, and if you follow that approach then the proof is very simple, because there you assume lots of things, okay. Let us just quickly recall before we go to the proof of this what we do. See, there what we do is that you look at two functions u and v from a b to r and assume that both of them are differentiable, okay. Assume that u and v both of them are differentiable, and then you look at this product formula, u v prime is equal to u prime v plus u v prime, okay. And then since all these functions are differentiable, they are in particular continuous also, so they are all Riemann integrable, and so since antiderivative of this exists, one can use the fundamental theorem of integral calculus here. And so suppose we use fundamental theorem of integral calculus, okay, what happens is this, that is one can get this integral a to b, let us say write it in the full form, that is u v prime dx, that is equal to integral a to b u v prime dx, so okay, u prime v dx plus integral a to b u v prime dx, okay. and then by using fundamental theorem of calculus, since its antiderivative is uv, u into v, so this becomes nothing but uv evaluated between b and a, that means this is nothing but ub into ub into vb minus ua into va, and then that is equal to this, okay. And so now we can say that u prime v dx is same as u v prime dx, okay. And remember we had also proved that this integral f d alpha, if alpha is a differentiable function and such that alpha prime is also integrable, Riemann integrable, then integral f d alpha in that case we had shown that is same as integral a to b f d alpha, we had shown that is same as integral a to b fx alpha prime x dx. That is how we could convert the Riemann-Stieltjes integral into Riemann integral. So suppose you use this notation, then this simply becomes, you can write this as integral a to b v du, okay. This u prime dx is du, and then this becomes integral a to b u dv, okay. So one can simply write this formula the same as this, okay, that is, okay, let us write this as integral a to b u dv is equal to ub vb minus ua va minus integral a to b v du, okay, and that is essentially same as this formula, okay. That is essentially same as this. If you take for example f as u and alpha as v, it is this, but the difference here is that you have assumed that u and v are differentiable, okay, you are assumed that u and v are differentiable, and that is why the proof, and then use fundamental theorem of calculus, and then the proof becomes very easy, okay. But here our assumptions are much less, okay, we are only assuming that these are functions of bounded variation, okay. And remember we had seen earlier that if a function has a continuous derivative, okay, then it is a function of bounded variation, okay. If the derivative is bounded, then the function is of bounded variation. So that is the special case of this, that is the special case of this, okay. Alright, let us now see how this can be proved in a general situation like this, okay. Let us go to the proof of this, and we shall be using again the integral as a limit of sum, that is we look at the given any integral, either this integral or that integral, we look at the corresponding Riemann-Stieltjes sum, okay, and once the function is integrable, the limit of the Riemann-Stieltjes sum goes to the value of the integral as the mesh of the partition goes to 0. That is the idea that we shall use, okay. So start with some partition, let us say p is equal to x naught x1 xn, suppose that is a partition of p, okay. I think it may be better here to draw this, suppose this is a and that is b, then this a is equal to x naught, so let us say x1 is somewhere here, x2 is somewhere here, etc, xn minus 1, and this last b is equal to xn, okay. Then to form the Riemann-Stieltjes sum, we choose Ti in each of this subinterval, okay. So choose some Ti, choose Ti belonging to xi minus 1 to xi. That means what? There will be some T1 here, some T2 here, etc, okay, and there will be some Tn here, okay. Alright, and so what is SPF alpha? That is sigma I going from 1 to n, f at Ti into delta alpha, okay. Let me write this delta alpha in the full form, delta alpha as alpha xi minus alpha xi minus 1, okay. Okay. Now what we do is that we also look at one more partition, okay. and that is a partition given by this T1, T2, Tn, okay. But only problem is this, till now for all partitions we had assumed that the, for example, a partition like this x0 has to be A and xn has to be B, but about this T1, T2, Tn we do not know that, okay. We do not know whether T1 is equal to A or whether Tn is equal to B, but that is not a problem. If it is not the case, we add those points, that is I add additional point, take T0 is equal to A and take Tn plus 1 is equal to B, okay. So consider A is equal to T0 and B is equal to Tn plus 1, okay, and consider this partition Q as T0, T1, etc., Tn plus 1, okay. Remember here also you have T0 less than T1, T1 less than T2, etc., etc., and finally Tn plus 1 is equal to B. So this is also a partition of AB, it is a partition of AB. Now what I do is that with respect to this partition, I write a Riemann's tilde sum corresponding to this integral. I write a Riemann's tilde sum corresponding to this integral, that means SQ alpha f, okay. Consider SQ alpha f. So that is again sigma I going from 1 to n, yes, n plus 1, right, there are n plus 1 intervals now, sub intervals now, I going from sorry I equal to 0 to n, okay. But the problem is that we also have to choose the points in between, in Ti minus 1 to Ti we have to choose the points, okay, and those points I take as xi, okay. Those points as, for example, here let us say here you have T1, here you have T2, in between the point I take as x1, okay, and this is what I do for all, okay, right. So I will take this as, so f at xi into, okay, this will turn out to be Ti plus 1 minus Ti. Oh, not Ti plus 1 minus Ti, so it should be other way, because we have alpha f, we want alpha f, okay. So alpha xi into f at Ti plus 1 minus f at Ti, okay, alright. Now it will help to write this, at least the first few terms of this in the full form, okay. Let me do it here, okay, yes, yes. In fact that was the whole point, we wanted to extend the class of monotonic increasing functions, that was the whole point of discussing the functions of bounded variations, okay, right, okay. So let us just write a first few terms so that you will understand what is happening here, okay. Let us look at this SPF alpha. What is the first term? It is f Ti, so f T1 into alpha x1 minus alpha x0, right. For I equal to 1, f T1 into alpha x1 minus alpha x0, etc., then plus f T2 into alpha x2 minus alpha x1, etc., etc. So what is the term corresponding to I equal to n? It is f at Tn multiplied by alpha xn minus alpha at x n minus 1, okay, okay. Similarly you look at SQ alpha f, SQ alpha f. Okay. It starts from I equal to 0, so alpha x alpha at x naught into f x1 minus f, sorry, f t1 minus f t naught, okay, f t1 minus f t naught. What is the second? Let me write one more term. For I equal to 1, it is alpha at x1 into f t2 minus f t1, etc. Okay. Let me just write the last term, plus alpha at tn into f at, sorry, alpha at xn, f at t n plus 1 minus f at tn. Okay. Okay. All right. Now suppose I take the sum of these two, S P f alpha plus S Q alpha f. Look at what is happening. Here you have the term f t1 alpha x1, okay, and here you have minus f t1 alpha x1, okay, it will be cancelled, right. Then similarly f t2 alpha x2, okay, okay, there will be that next term f t2 alpha x2, it will be minus f t2 alpha x2 here, okay. So several terms will cancel. What will remain? For example, here you have alpha x naught f t1, here you have minus alpha x naught f t1, okay. So what will remain is the alpha minus alpha x naught f t naught, corresponding to that there is nothing here, okay. And finally here also f tn plus 1 alpha xn, corresponding to that also there is nothing, okay. So so if you take the sum of that, what remains is this, that is minus alpha x naught f t naught, and then plus alpha xn f tn plus 1, okay, right. But again now remember the fact that x naught and t naught both are A, okay, xn is B and tn plus 1 is also B, okay, that is how we have chosen, okay. So I can rewrite this whole thing as SP f alpha, that is equal to fb alpha b minus fa alpha a, and then minus sq alpha f, okay. All right, okay. Then we know that this integral f d alpha exists, that is our assumption, okay, integral f d alpha exists. So now this is a Riemann Stieltjes sum corresponding to this integral, okay, and so this as mesh of the partition P goes to 0, okay, then this will converge to integral a to b f d alpha, right. Similarly as the mesh of the partition Q goes to 0, mesh of the partition Q goes to 0, that SQ alpha f will converge to integral a to b alpha df, okay. Now the only question is this, can we say that whenever mesh of the partition P goes to 0, mesh of the partition Q also goes to 0, can we say that? How are the mesh of P and mesh of Q related? You can say, for example, if suppose you take T2 minus T1, okay, okay, obviously it is smaller than x2 minus a, okay. So similarly if you take any Ti minus 1, if you take any subinterval of the partition Q, you can say that it will be less than, its length will be less than or equal to sum of the two consecutive intervals, that you can always say, okay. So I can say this, that the mesh of Q is less than or equal to 2 times mesh of P, right. I mean this may not be a very good estimate, but it is certainly true, okay, right. So all that we need is this, that whenever mesh of P goes to 0, mesh of Q also goes to 0, okay, right. And hence, okay, so okay, so let mesh of P tends to 0, then mesh of Q also tends to 0, and what happens is SP f alpha tends to integral a to b f d alpha, and SQ alpha f tends to integral a to b alpha df, right. Okay. And so as mesh of P tends to 0, this left hand side goes to integral a to b f d alpha, and this term will go to integral a to b alpha df, and this will remain as it is fb, because that has nothing to do with the partition, okay. That is true for all the partitions. So in the limit we get this formula for the integration by part, okay. Okay. Now in addition to what we have said here, let us assume a few more things, okay. Suppose I further assume that this alpha is continuous and f is monotonically increasing, okay, alpha is continuous and f is monotonically increasing, then I can apply, then this will be a usual Riemann-Stieltjes integral, and I can apply mean value theorem to this term, I can apply mean value theorem to this term, and then we will see what happens to this whole thing, okay. So let us write that as a corollary. So what we mean to say is that in addition to the above hypothesis, assume that alpha is continuous, and f is monotonically increasing, in AB, okay. Then okay, then what happens I will write little later, okay. First we shall see what we are aiming at, okay. See, if you recall the first mean value theorem of integral calculus, what we said there, that if you look at the integral a to b f d alpha, if f is continuous and alpha is monotonically increasing, we had shown that there exists a point C, in the interval such that this integral is same as f at C into alpha b minus alpha a, okay, right. That is what we had called the first mean value theorem of the integral calculus, okay. Suppose I apply that to this term here, now I am assuming that alpha is continuous and f is monotonically increasing, okay. So we can apply that to this term, okay. So let us say by applying the first mean value theorem of integral calculus, okay, because there exists some point C in AB there exists some point C in AB such that what should happen, integral a to b alpha df, what should be this, just imitate this, okay. Now the roles of alpha and f are interchanged, okay. So this should be alpha at C multiplied by fb minus fa, okay, right. So alpha of df, that is equal to alpha at C multiplied by fb minus fa. Okay. Up to this we have done nothing new, okay, that we have just applied the first mean value theorem. Now you substitute this value here, okay, now you substitute this value here, okay. So what happens, we say integral a to b f d alpha, integral a to b f d alpha, that is equal to, okay, those first two terms will leave as they are, fb alpha b minus fa alpha a, and then minus, for this minus integral alpha df I will write this value, okay, minus integral alpha df. So minus alpha at C into fb minus fa. Okay. Yes. Right, f of b into alpha of b, that is right. Okay, all right. Now we will combine in slightly different manner, okay. You have fb here and here also, so we will combine these two terms. So what we will get is fb into alpha b minus alpha c, okay, fb into alpha b minus alpha c, right, and then what remains, is minus fa alpha a here, so minus fa into again alpha a minus alpha c, okay, okay. So combining all this, what we can say is that then I will come back to this, okay. Then there exists C in AB such that integral a to b f d alpha, this is equal to fb into alpha b minus alpha c minus fa, or if you want you can change it slightly. If I make this plus sign here, then that will be alpha c minus alpha a, okay. So that is how it is customarily written, plus fa into alpha c minus alpha a, okay, plus fa into alpha c minus alpha a. So this conclusion that there exists, that is whenever f and alpha satisfy all these conditions that I mentioned here, there exists a c such that integral a to b f d alpha turns out to be fb into alpha b minus alpha c plus fa into alpha c minus alpha a. This is what is called second mean value theorem, okay. This is called, this whole thing, that is there exists c satisfying this, this is called second mean value theorem of integral calculus. Okay. So while discussing the first mean value theorem, I had commented that why it is called first, because there is something to follow, okay. So now this is the second mean value theorem, so that is the idea, okay. Okay. Alright, then there is one more thing that about the integrals that we need to discuss, and maybe with that we can close this discussion on integration, and that is what is called change of variable formula. Again something that one uses quite extensively in practice, change of variables formula. okay. Here also let us okay, to make the matter simple, let us take the function to be continuous, okay. Suppose, and let us talk only about the Riemann integrals instead of Riemann-Stieltjes integral, okay. Suppose f from AB to R is continuous, okay, and let us say and phi from AB to R, phi from AB to R is okay, this also let us take continuous, and continuous and strictly monotonically increasing, strictly monotonically increasing. Okay. Now what is the implication of saying that it is strictly monotonically increasing? Okay, what is meant by strictly monotonically increasing? That whenever x is less than y, phi x is strictly less than phi y, okay. So in particular it means that the function is 1 1, right. Once you say it is strictly monotonically increasing, it means that the function is 1 1, and hence we can talk about the inverse function, okay. Inverse, suppose you take this phi will map AB to the interval phi a to phi b, okay, it will map the interval to phi a to phi b, and so I can talk about the inverse function, okay. Suppose that inverse function is what I call psi, okay. So let psi from, okay, let us take what will be the interval, it will be the interval from phi a to phi b, okay. I can say phi a to phi b to R, but actually it is phi a to phi b to AB, right, okay. Let us say psi from AB be the inverse function, inverse function, okay. Then remember in a general situation we may also have to make the statement that f is Riemann integrable and whatever occurs is Riemann, etc., but all that is not necessary because f is continuous and we already proved that the continuous functions are Riemann integrable, okay. So what I want to say is that in that case integral a to b fx dx, this will be transferred to integral from phi a to phi b, phi a to phi b, f at psi y, f at psi y d psi y, okay. Again this is also something that is fairly easy to prove if you assume that these functions involved are differentiable, okay. Then one can use fundamental theorem of integral calculus and then the whole proof will become very easy because there it follows merely by chain rule, okay, right. And then for example then this d psi y will be nothing but psi prime y into dy, and that will be the, and then all that remains is to say that suppose you look at this function f at psi y, and then its derivative is nothing but f prime at psi y and multiplied by psi prime y, okay. So that's all is required, okay. So for example suppose you look at suppose you assume that psi is differentiable, then by using a standard application of fundamental theorem of integral calculus all this becomes very easy to prove. Since I have done it for several other theorems I will not discuss that thing now here, okay. We shall just see this case how we have to prove. But since we are now discussing the general case we have to represent each of this integral as the limit of a sum, okay, and that is what we shall do. And so we shall discuss, we shall start with some partition which represents this integral and look at the corresponding partition here, okay. So okay, so let us say let P be as usual this a is equal to x naught less than x1 etc., etc., less than xn that is equal to b be a partition of AB. Okay. And when we proceed with the proof, you will also understand what is exactly the implication of assuming that f is continuous and phi is continuous. Okay. Now to consider the Riemann sum, we have to look at some points Ti in the subinterval Ti xi minus 1 to xi. So choose Ti belonging to xi minus 1 to xi. Then form the Riemann sum RPF, that is same as sigma I going from 1 to n FTI multiplied by, okay, instead of delta xi I will write it as xi minus 1, xi minus xi minus 1. Okay, all right. Okay, now let us see the first implication. Okay, what did we assume about phi? We assumed that phi is strictly monotonically increasing. Okay, phi is strictly monotonically increasing. So if I look at phi at x naught, that must be strictly less than phi at x1, okay, and that must be strictly less than phi at x2, etc. So what we can say is that phi of A, which is same as phi at x naught, this is strictly less than phi at x1, etc., etc., strictly less than phi of xn, and that is equal to not b, phi of b. What is the meaning of this? It means that this phi x naught, phi x1, etc., that is a partition of this interval phi a to phi b. That is a partition of this interval phi a to phi b, right? Okay, okay. If we want to give some notation for this, okay, we can call this phi, this we can call this as y naught, this as y1, etc. Okay. That is in general call let yi be equal to phi xi. Okay, okay. Then what we want to say is that then this y naught, y1, yn is a partition of this interval phi a to phi b. Okay, all right. Okay, that is said about this xi's and yi's. What about ti's? If ti is in xi minus 1 to xi, okay, then phi of ti must be in the phi of ti must be in the phi of yi minus 1 to yi. Okay, so this means phi of ti belongs to phi of xi minus 1 to phi of xi, which is same as yi minus 1 to yi. So if I want to think of Riemann integrals of something, we can take this point phi at ti and multiply that by the length of these intervals. That is possible, right? That is possible. Okay, all right. Now which is the function? Okay, and that is the clue that you get from here. Okay, we are not looking at the function phi, but now the function, okay, function psi is from phi a to, because remember we want to now look at the integral on this interval phi a to phi b. So there should be some function which is defined on that interval. Okay, so that interval we take the function this f composed with psi. Okay, see psi is defined on, okay, remember psi is defined from phi a to ab and f is defined from ab to r. So f composed with psi will be defined from phi a, phi b to r. Okay, so look at this. So just okay, f composed with psi, this will be defined from phi a, phi b to r. okay. And what we want to know is that we want to look at the Riemann-Stieltjes integral of this function f composed with psi with respect to this function d psi. Remember here that we have assumed that phi is strictly monotonically increasing and psi is its inverse. Does it follow that psi is also strictly monotonically increasing, right? Okay, so there is no problem. Okay, so if you look at this now, we can express everything now in terms of psi. Okay, for example, if you look at this sum here, okay, this okay, let us leave RPF. What is this? That is nothing but sigma I going from 1 to n. Okay, for the time being let me write it like this, FTI into xi minus xi minus 1. Okay, all right. Okay, first things, can I write this xi as psi yi and xi minus 1 as psi yi minus 1? Fine. Okay. Okay, so this is same as sigma I going from 1 to n. This term I will write later. Okay, this is nothing but psi yi minus psi yi minus 1. Okay, all right. Okay, only question is how do I write this f at ti? Okay, now remember here phi of ti belongs to this subinterval yi minus 1 to yi. Okay, I have not given any name for this phi of ti. Let us give it now. Okay, let us say that suppose I call this as si. Let si be equal to phi ti. Okay, let si be equal to phi ti. Right, that is same as saying that ti is equal to psi of si. Right, that is same as saying that ti is equal to psi of si. Okay, so suppose I use this notation, this becomes f at psi si multiplied by psi yi minus psi yi minus 1. Okay, all right. Now what can you say about this sum here? It is nothing but the Riemann-Stieltjes sum of this. I have computed f composed with psi at si and multiplied that by psi yi minus psi yi minus 1. Okay, and si is a point which lies between yi minus 1 and yi. So this is nothing but the Riemann-Stieltjes sum of the function f composed with psi with respect to the function psi. Okay, so in other words, and with respect to this partition here. Okay, with respect to this partition here. Okay, again we have not given any name to this partition, let us give it now. Okay, suppose I call this partition q. Okay, right. Okay, then this is nothing but s function is f composed with psi, function is f composed with psi, sorry, first I should write partition s q f composed with psi psi, right. Okay, okay, all right. Okay, now we know that f is continuous. Okay, so this RPF will go to integral a to b fx dx whenever mesh of the partition goes to 0. Okay, all right. Similarly, if f is continuous, psi is also continuous, f composed with psi is continuous. Okay, and psi is monotonically increasing. Okay, so this integral also exists, that is integral a to b f psi y, that also exists. Okay, and this Riemann-Stieltjes sum will also go to this integral provided mesh of the partition q goes to 0. Okay, now that is the only question, whether we can show that whenever the mesh of the partition p goes to 0, mesh of q also goes to 0. Okay, okay, and that is exactly where we make use of this hypothesis that phi is continuous. Okay, phi is continuous, it is a closed and bounded interval, hence it is uniformly continuous, hence it is uniformly continuous. So what I can say is that given any epsilon, you can find a delta, okay, such that whenever let us say xi minus 1 is less than delta, phi of xi minus phi of xi minus 1 is less than epsilon. Okay, so in other words, whenever mesh of the partition p goes to 0, mesh of the partition q also goes to 0. That follows from the uniform continuity of phi. Okay, that follows from the, so let us simply write this, that is, since we can say that since phi is uniformly continuous, continuous, we can say that okay, we can say that for every epsilon bigger than 0 there exists delta bigger than 0 such that if mesh of P is less than delta, then mesh of Q is less than epsilon, okay, right, because mesh of P is less than delta means what, for each I xi minus 1 is less than delta, okay, then phi xi minus 1 must be less than epsilon, maximum of those values is mesh of Q, so mesh of Q must be less than epsilon, okay, alright. So in other words, if mu of P goes to 0, mu of Q goes to 0, okay, that is that, in fact that is what this means, that is if mu of P goes to 0 then mu of Q goes to 0, okay, and that is the end of the proof, okay. So we let mu of P goes to 0, this will tend to integral a to b fx dx, okay, this will tend to integral a to b fx dx, and this will tend to integral phi a to phi b f composed with psi d psi, right, okay, all right, okay. And that is what is said here, okay, that is in the limit integral a to b fx dx should be same as integral phi a to phi b f of psi by d psi by, okay, all right, okay. So with that we sort of finish the main points of the usual integrals that we wanted to discuss. There is only one small points which we need sometimes, so I will just mention it in passing, but we shall not go into too many details of that, okay, and that is what is called improper integrals. I mean the name itself suggests that there is something less than here than what we have discussed so far. In other words, what we have discussed so far were proper integrals, okay, and some property is not satisfied here, so these are improper integrals. And what is that property? Okay, let us stick to the Riemann integrals, okay, for this discussion. We have always assumed that the interval a to b is of finite length, that is first thing, okay, and we have always assumed that the function is bounded, function ab to r is bounded, okay. If one of these assumptions is not there, that is either if you take the infinite length, okay, for example a to infinity or minus infinity to b or minus infinity to plus infinity, that kind of intervals, that is one possibility, that is interval is of infinite length. So it means that we cannot do several things which we did. For example, if you would have seen in the several proofs that we have assumed that whenever a function is continuous it is uniformly continuous, that we could say because the interval was closed and bounded. If it is an interval of the type a to infinity we cannot do that sort of thing, so that is one possibility. Other thing is that function may not be bounded somewhere, okay. For example, it may be of the type interval may be 0 to 1 and a function may be of the type 1 by x, then near x equal to 0 it is not bounded. So if any such thing happens then it is called improper integral. And how this is done or how those improper integrals are dealt with, basically we convert them into a series of proper integrals, that is the whole idea, okay. Whatever be the case we convert them into a series of proper integrals. So for example let us just take this case, symbolically it is written like this, integral a to infinity fx dx. From the theory that we have done so far this is meaningless, okay, because we have not defined what is meant by this. But suppose the following happens, okay, suppose for every y bigger than or equal to a, f is Riemann integrable, in the interval a to y, okay. Suppose this happens for every y, okay, right, then I can talk about this integral integral a to y fx dx, right, because we have assumed that it is integrable in this interval a to y, okay, right. So it means this will define a new function in the interval a to infinity, okay, that is for each y. Suppose I call this as a, we can say that define f from this interval a to infinity to r by this suppose I call it big F of y. So this is defined for y bigger than or equal to a, okay, and what do? We consider the limit of this as y goes to infinity, right. This is a function of y, we consider the limit of this as y goes to infinity. If this limit exists, we say that this improper integral converges, right, okay. If the limit exists, we say that this improper integral converges, and whatever is the value of this limit, that is taken as the value of this integral, okay, right. That means this is nothing but the value of this limit of fy as y goes to infinity, okay. So in symbols we can write this as, this is same as limit as y tends to infinity integral a to y fx dx, okay. Of course this may or may not exist, this limit may or may not exist, okay. Only when the limit exists we say that this improper integral converges and its value is given by this limit. If this limit does not exist, then we say that improper integral diverges, and once it diverges there is no question of a value, okay. Alright, we will stop with that for today.